Extending the Hahn-Banach theorem into complex vector spaces is more than a technicality. It is a requirement for the mathematics of quantum mechanics and operator theory. In the real-valued version of the theorem, we can take a linear functional from a small subspace and extend it to the entire space, as long as it remains bounded by a sublinear function p of x. This logic fails in a complex setting because complex numbers lack a natural ordering. There is no way to state that one complex number is less than another, which renders the standard real-valued inequality meaningless. To fix this, we redefine the bound. We instead require that the absolute value, or the magnitude of the complex functional, stays below the real-valued sublinear bound. Using the absolute value restores the bound components, f1 and f2. Because the functional is complex linear, the imaginary part is actually tied to the real part. By evaluating the functional at ix, we can see that the imaginary component is just the real component evaluated with a phase-shifted input. This means we only need to extend the real part using the standard theorem. Once the real extension is established, the full complex extension is built by simply plugging that real part into this formula. Leveraging complex linearity, the imaginary part of the extension must follow the real part, effectively reducing the complex problem to a real one. Now we must verify the most difficult part, that the magnitude of this newly constructed functional actually respects the absolute value bound. We use a polar form trick. By multiplying the output by its complex phase inverse, we rotate the vector until it lies purely on the real number line. Once the output is purely real, we can apply the real-valued bounding rules directly, proving the magnitude stays within the required bound. This geometric rotation is the key mechanism that bridges complex values back to solvable real inequalities. In normed spaces, this theorem guarantees that when we extend a functional, its operator norm, or its maximum stretch factor, is perfectly preserved. The extended functional remains as bounded as the original. This leads to a fundamental consequence for dual spaces. For any non-zero vector, we can always construct a bounded linear functional to isolate it. By extending a functional from a one-dimensional subspace, we prove the dual space always contains enough functionals to distinguish between any two vectors. This existence guarantee provides the mathematical assurance needed to define observables in quantum mechanics. It ensures that the complex spaces used by physicists like Erwin Schrödinger possess the functionals required to extract real-valued measurements from quantum states. To see more step-by-step proofs from the world of functional analysis, subscribe to the channel. The complex Hahn-Banach theorem is the mechanism that ensures our mathematical models of complex systems are always capable of producing observable real-world data.